Yes?
Can we start?
Sure. Okay.
Okay, good afternoon. So we're coming to the second session in our winter school. So we're going to have Simone Professor Simone Pigolotti to have this second lecture. So, okay, please start, Simone.
Okay. Thanks again. So this morning we'll be talking about some general ecosystem patterns and some of the phenomena that can emerge when you have space to this stochastic system dynamics. And in this talk, I'll discuss two things essentially. So both are related to this phenomenon which is called Bet-hedging, and I will explain what this refers to. But then I will present two different recent projects. One is an external collaboration with marine biology from NTHU in Denmark, and it's a complete case study of populations of jellyfish. And in the second part of the talk, I will discuss a recent extension that we developed in my group of the theory of fisher waves, which is the theory of how populations expand and colonize new territories, generalized to cases where you have multiple populations adopting multiple strategies. So first of all, I'll introduce this concept that will be one of the leitmotifs of this presentation, which is bet-hedging. So the idea of bet-hedging it has been introduced in the context of gambling, but it has an importance, first of all, for investment. So this idea has been had deep consequences for developing of investment portfolio. And more recently has been connected with the phenomenon occurring in evolution and ecology. So the interesting paper that I'd like to recommend is this paper by Kelly from 1956. Kelly was a colleague of Shannon, the Shannon of information theory, and he realized that there was an analogy between the theory that Shannon described for describing information of probability distribution with gambling with an uncertain situation. And just to give you a sense of, sorry, and this slide. So just to give you a sense of what this is, so imagine that you have to bet on the outcome of tossing a coin. So let's say you invest some of your money, and if if the coin toss is head, your money is doubled. Otherwise, you lose everything that you have bet. So in this case, there is a mathematical theory, but also common wisdom should tell you that you should not play this game, because if you play it, after a while, you will lose all your money. That should be pretty obvious. So the most interesting case is, imagine that the coin is not fair. So imagine that you know that the probability of head is slightly higher than 50%. So maybe 60% or something. Then in this case, you might want to invest some of your money on this game, but at the same time, you don't want to invest all your money in this game, because there is still a finite chance that tail will be the outcome of the game, and then you would have lost everything. So the most natural way to quantify a risk is to imagine you play the game many times, and let's say that each game you invest a fraction of what you have accumulated up to that point. And what you want to know is, suppose that you know the bias of the coin, which is the probability that a head will happen at any given round, what fraction of the capital you should bet at each time. So this is essentially the mathematics in Q1. So this dollar time t is your capital at time t, which is your capital at time 0, and then every time a head will, the result will be a head, you will have one q, so your capital will be multiplied by 1 plus q, and every time there is a tail, your capital will be multiplied by 1 minus q. So your capital at time t will be the capital at time 0 multiplied by 1 plus q, the power of the number of times a head happened, multiplied by 1 minus q to the number of tails, right? And then I can bring everything to exponents and say that if p is the probability of a head for large t, n head it will be t times p, and the number of tails will be t times 1 minus p, and so you would have this expression that you see in the second line. If you maximize this expression with respect to q, which is how much do you invest, you will find that q should be equal to 2p plus 1. So this is consistent with the fact that if p is 1 out, q is 0, so you shouldn't play the game to keep all your money. But again, if there is a small bias, then you should invest some small fraction of your money in the game. And the interesting thing is also you can compute the factor. So what is the exponential growth rate of your capital on average? So you just need to replace this value of q in this expression, and you find that this growth rate will be log 2 plus p log p plus 1 minus p log 1 plus minus p, and this expression is quite reminiscent of, say, statistical physics and information theory, because it's the difference between the entropy of a fake coin, which is log 2, minus the entropy of the coin you have. So in other words, how much you can gain from the game is related to the information you acquire by knowing that the coin is balanced. That's essentially the result, and it's much more than. So in some sense, if I know something about what's happening in the game, that translates into increase of capital, and this is related to the information quantified by Shannon entropy. This is the basic idea. So this idea, as I said, has been generalized to population, and here the idea is that you can imagine to have a population which can appear in different phenotypes. So this is a sketch of the plate, and this is taken from a paper by Elkas and Stan Library in 2005. So essentially, imagine that this population can have different phenotypes and is subject to a variant environment. So the environment can be in different states. You can imagine different temperatures, different nutrient concentrations, and so on. And different phenotypes are more or less adapted to these different environments. So let's say the blue phenotype is optimal in the blue environment, and so on and so forth. So there are two things that this population can do. It could simply respond to the environment. So at each time, it could measure what the environment is and start changing its state or producing more offspring of the type which is optimal in that given environment. So this would be, for example, well, I don't know, different kinds of adaptation. So bacteria can do like expressing different enzymes to process different sugars depending on where they are in the environment. No. But the other thing the population could do is stochastic switching. So it could, even if the blue is the optimal environment, it could express the other phenotype with a small probability, and this would be convenient because if the environment switch, then these phenotypes will be already present in the population, and they will be automatically selected. So this would be essentially the equivalent of in the gambling case of diversifying the investment. So because diversifying investment serves the purpose that if the state of the market changes, I would still have some assets that that can be better from which I can profit better if the state of the economy changes. And the other advantage in ecology is that stochastic riches does not require sensing the environment. So for bacteria, sensing the environment is a costly operation, and if you just stochastically switch at random, I can save this energy. So this theory again has been applied mostly to microorganisms, but the theory I present to you today is about some bigger organisms which are jellyfish. So these are the so-called moon jellyfish. This is in a gulf in Denmark, so my collaborators are in Denmark. And so jellyfish are known for a number of reasons, especially because of their harm to humans if you encounter some of them on the beach. But what my collaborator explained to me is that, in particular, this kind of this family of jellyfish, called schizoform jellyfish, have a rather interesting life cycle. So first of all, they have two reproductive modes. One is sexual, where it's so-called polyps, which are small organisms that live in the bottom of the ocean, can spawn into juvenile and then become medusa, which are the actual jellyfish that we see in the sea. And then the medusa will reproduce again and form these polyps. But polyps can also spawn, so just generate other polyps, and this is the asexual mode of reproduction. So they will just reproduce itself without needing for mating and without undergoing the medusa stage. So there is these two different modes of reproduction. And the interesting thing is that even if we focus on the asexual life cycle, so forgetting about the medusa, which are the actual jellyfish, there are three different asexual reproductive modes. So one is what I just described. So the polyps can just spawn continuously and generate other polyps. This is drawn with this number 1. A second one is that they can form cysts, which are pretty hard bodies, which are like seeds. They just stay in the bottom of the ocean. They can stay there for a long time, potentially for years, and then spawn polyps again. And the third one are these so-called planaloids, which are similar to seeds, but they are very light and therefore can be transported by sea currents. And again, after being transported, they can spawn and generate other polyps. So the interesting thing that our curiosity is that if you look at different species of jellyfish, some of them have available all these three modes, some of them have only one, and some of them have two of them. So there seems to be quite diverse range of combination of evolutionary strategies. And we wanted to have some kind of conceptual model to understand why this is the case. And this is the model we developed. So this is essentially a resume of the model, and then I will describe each stage of this model. So the model has a discrete generation, which are these dashed lines. And at the beginning, there is a population of n polyps. And the strategy of these polyps will be to essentially divide their offspring into these three different reproductive modes. So we assume that in principle, these polyps can do all of these three things, and they have to allocate their offspring into these three resources. So we call FP, Fn, and Fc the fraction of offspring that will go into planaloids, polyps, and cysts. Okay? So this is what we want to, in the end, optimize. So this is essentially the polyp economy. Just they have these three different assets, and they want to decide how they need to allocate the resources into these three. So one first ingredient is that these three strategies have different growth rates. So in particular, the polyp itself are the fastest growing because they can spawn continuously, whereas the other are slower, so they can spawn only at the end of the season. So there is this factor R that takes into account the growth rate of these three strategies. We don't know exactly this number, but we know that for planaloids and cysts is certainly much smaller than for polyps. So this means that essentially if you have this population, you have a fraction FP, RP of planloids, which is how much they allocate to planloids multiplied by the growth rate, and similarly for the other two strategies. So these three strategies do three different things. So the idea is that the polyps are just reproducing. The planloids can diffuse, so we have a spatial model, and this is the only strategy that can colonize nearby space. And instead, the cysts do not spawn at the time, but they are sitting on the bottom of the ocean, and they can hatch later, for example, the following year or later in the future. So let me just go into the details of all this page and just detail how it works. So first of all, we have the beginning of the season. So the sea for us is a square lattice. So again, we consider a spatial model. So we have a population in each of these lattice sides. And since we want to see what is the optimal strategy, we mentioned that we have competition between two populations. So we have two different kinds of polyps. One would be the wild type and one would be the mutant. And the idea is that the mutant will have the same growth rates, but only a slightly different allocation in these three strategies. So only this fraction will change for the wild type and the mutant. So each one would have a fraction of polyps in one of these boxes. And for convenience, we just normalize it. So this fraction is something one. And at the same time, there would be a fraction of cysts, which are distinct cysts on the bottom of the ocean, which we essentially got from the previous generation. So these things are long-lived, and the leaves of every year. So the next step would be reproduction. So these polyps will generate this local budding, which will be just the polyps, so they just generate more of them. The motile buds, they also will be spawned at the same season, but this one will be spread among the neighboring patches who will undergo diffusion. And the last one would be the cyst. So the cyst that would first go into this cyst bank, which is age, and some of them can spawn again. So the idea is that there is a buffer of cysts. You can produce them, and some of them will spawn, but some of them will stay in the bottom of the ocean. So these are the equation is actually consistent of a linear population. Okay, so the next step would be competition. So at the end of the year, the cysts that hatched the polyps and the planloids in the site are summed together, and this will constitute the population at the end of the year. And the effect of competition is to just renormalize this population. So at this point, since we have the sum of all these effects, the two populations will be much larger than one, and we just divide by the total, so that we just normalize to the one in the sum. So last but not least, we have a round of extinction. So these polyps are typically can spawn only if the temperature and salinity of the sea are in a given range, and plus they can be predated by medium to large size fish. They have a high clearance rate, which means that they can arrive and just eat everything that is there. And so we model all these effects by saying that with a given probability, we just kill everything that is in one patch. So both the wild type and the mutant will be killed, and the only thing that is surviving is the cyst, because the cysts are hard, they sit in the bottom of the ocean, and the predator cannot eat them. Okay?
Question, Simone?
Yes.
Yes. When you write down the growth, it's continuous growth, or is there any carrying capacity? The growth term.
So the growth is not exponential because at each time you normalize to one.
Oh. Okay.
So you just need to keep track of the fraction. So the way you can imagine is that if you are in a given box, so in a given patch of the ocean, you want to maximize your offspring. So to maximize your offspring, you should reproduce locally. But the problem with reproducing locally is that if there is an extinction event, that will kill all your offspring. So there are two ways in which you can escape from this. You can either disperse in all the neighboring boxes, and therefore you spread the risk of this extinction. So at least one of these boxes there will be no extinction, and those population will survive. Or you just put your population in this bank in the bottom of the ocean, and those are completely safe. So until they are sitting there, the predators cannot attack them. So then when the predator is gone, these ones can spawn, and then and they are safe. Does that make sense?
Yeah, okay, thank you.
Okay. So, yeah, and this is repeated on and on. So first of all, if you have two, as I said, we did this as a competition experiment. So we started with two populations which has the same fitness for the two strategies, but they just have different allocations in these resources. And we just monitor in time the average density of polyps in the entire sea. And what you see is that after a while, so this is the number of steps, one of the two will prevail. So one is going to 0 and the other is going to, in this case, 0.5 because you have extinction. So it's not 1, so it will be 1, the average in patches without extinction, but since some of them are killed, the average is not 1. So this is an example of competitive exclusion. So one of them is fitter because they have a better allocation in these strategies. So we can do an evolution experiment. So we run this simulation, and so if one of them has a higher fitness, which is data as the wild type, we pick another mutant which would have the same strategy plus some small difference, and make it compete with the mutant and see if that's better, and so on and so forth, until we find the fittest strategy. So here in the figure you see the relative allocation in these three strategies, and now this evolution experiment optimizes this allocation. And so you can see that in this simulation, after about 300 fights between the mutants and the wild types, this goes to some kind of steady state, which means that this wild type that we found cannot be replaced by any mutant, and therefore it's evolutionized. So we wanted to test whether this is the case, and so you can. So if you have three strategy, there is a way which is common in evolutionary game theory to represent this strategy, which is to plot these three fractions on a triangle, which again represent the relative weights of these strategies. And so what we did was to run this competition experiment starting from different points, which are different colored lines in this figure. And what we found is that after many rounds, all of them evolve to the same point on this triangle, which is the black dot in the center of this triangle. So this means that indeed this solution is evolutionarily stable, which means independently on the initial condition, evolution will still find the same solution, and this is stable, right? So now what we wanted to understand is how the evolutionary stable strategy depends on the parameters of the model.
Simone,
And
may I
yes?
have a quick question? So this is a result of simulations?
Yeah, it's all simulations. We have unfortunately little analytical results. I mean, this is actually a model we found to solve, but we actually ended up just getting a numerical sense of how it was.
Does the result depend on system size? Or, the extinction is related to the system size?
System size is not so important. We tried that. There are the parameters that are important are the fitness of the three species and the extinction rate. So this is what I'm showing you in this slide. So this is maybe a little bit complicated to read, but essentially you should see that the shades of brown are the extinction rate. So dark means high extinction rate, and pale is a small extinction rate, and shades of purple are the relative thickness of cyst and motile, which are these planoids. So dark purple means that the motile strategy has a higher thickness, and more like red means that cyst has a higher thickness. So what you see here is that essentially, I mean, the lines are different, but what happens is that if the extinction risk is 0, then you would have a pure strategy of just producing polyps. And this makes sense because polyps have the highest growth rate. So if there is no risk, you should not bother investing your resources into the other strategies, but just use this one, which is the one that has the highest weakness. Then if you start increasing the extinction risk, you will either start producing motile or these cysts. So you will have two strategies. This will be being on one of the lines, one of the sides of this triangle. And if you increase the extinction risk even further, then you will find a mixed strategy with all three strategies included. So you will find yourself in the middle of the triangle. And lastly, if the extinction risk is very high, you will end up with a strategy where you only produce cysts, because this is essentially the safest of the three strategies, because again, it's the only one that can survive these extinction events. We also tried other things, for example, considering the case of partially correlated extinction, and this is relevant for the ocean. So instead of picking them in a Poissonian way, we would have big patches where extinction occurs, and this effect, increasing the range of extinction, would further push the equilibrium towards more cysts. And this again makes sense because if there are discorrelated extinction, it's harder to escape from them by diffusing, because if there is an extinction in your cell, it's likely that there is an extinction in neighboring cells. And so the only way to escape this event would be to, again, use this other strategy where there are the seeds, and the seeds would require extinctions. So just a conclusion of this part, this simple model shows that in this kind of ecological situation, you can have coexistence of multiple strategies, even if some of them have a very different thickness from each other. It's consistent with some observation in real systems. So for example, there are no species of jellyfish that employs only polyps in the sea, but if the jellyfish are grown in a tank and provided a lot of fish, so of course that would be an extremely stable and an extremely safe condition, they can slowly shift their strategy and evolve towards a situation where they only produce polyps. So this is something that is explained in our model. The other thing is that generalists, so jellyfish that tend to grow in a diversity of environment, typically employ all three reproductive strategies. This is again consistent with what our model predicts. And if in again laboratory experiments jellyfish are exposed to predation or starvation, they tend to produce more cysts, and this is again what our model predicts. The last thing, which is actually something that would be interesting to characterize better from an analytical point of view, is this trade-off between these two basic strategies. So the idea of if there is a physical environment, you can escape in space by diffusing, or escape in time by going into this dormant mode and then spawning again. And it's really like we have numerical evidence about how this trade-off works, but it would be nice to get characterize it better from a mathematical point of view. So yeah, the second part of my talk will be more about some general theory, and it concerns the idea of range expansion. So range expansion is something very important for many species, including us, So it's known that Homo sapiens was born in Africa, and on a time scale of several hundreds of thousands of years conquered the entire Earth, and during this time scale, evolution occurs and competition with other species occurs, and so this is one of the most important processes in ecological dynamics. So again, I showed you this example in this morning talk, which is the example of a growing colony where a neutral competition occurs. And now I would like to just discuss a bit the simplest models to discuss to model growth, spatial growth of our population. So the first model that I want to introduce is again a Biophysics model, which is the logistic model. So C we interpret as the concentration of our population or concentration of our mutations in a population. And according to the logistic model, there is a parameter that accounts for exponential growth, which is this A, and another parameter which will give you a saturation effect, which is related to competition. So if you solve this equation, you will get something like this figure, so it's like this smaller shape. You will have an exponential growth for short times and then a saturation effect. And what's less known perhaps is that this model is not only a simple model, but it's also a rather precise quantitative model. So this is the points you can see is just growing a colony of yeast in a test tube. And if you look at the concentration as a function of time, it's very, very well described by this simulation. So again, here there is no space, but the other thing one can do is to consider the same dynamics but in space. And so what you consider here is a population which grows with the logistic equation in a given position, and then can also spread in space according to a diffusion equation. And that would simply do the Fisher equation. And basic result of the Fisher equation is that you would get a propagating front, and the propagating front depends on a combination of the diffusion constant and the exponential growth rate, which is this parameter S. So the particular velocity is twice the square root of V times S. So the other thing that I want to introduce is the idea of adding fluctuations to these waves. So to do that, we need to go back to the idea that populations are made of individuals, so they are never infinite. And one can derive this continuous equation from a discrete description by imagining that you have a discretized space. At each position in space, perhaps you have two different populations. They can diffuse by moving among different locations in space. They can reproduce and they can compete with each other. So if you do that, what you would end up with is a continuum limit, which would be a generalization of the Fisher equation, including for stochastic fluctuations. So the last term in this equation is a noise term, which again takes into account the fact that the population size n is not infinite, and therefore this demographic process induces some fluctuation on this wave. So essentially, the phenomenology of this model it can be understood in this way. So you have essentially two inverse time scales in this process. One is exponential growth rate, and the other one is the inverse of the population size. So if S is very large compared to the inverse population size, then the dynamics will be very similar to the Fisher wave. So now, instead of plotting the wavefront, I'm making a heat map of the solution as a function of time. And you can see in the left panel that you have this almost deterministic front propagating at a constant speed. And instead, if S is very small, you would get these very different dynamics where you would have locally either 1 or 0. So either population is fixated or is absent, and then you would have diffusion of these boundaries. So this scenario is much more similar to what we described with neutral theory, where everything is stochastic and essentially the physics is related to the physics of Lessing random walkers. So this is just a brief introduction to these noisy waves. And what we want to do now is to consider a wave where the underlying population has access to multiple strategies and is subject to varying environments. So to do that, we just take the Fisher equation and we just assume that the growth rate depends on possibly on space and time. So in particular, we imagine that the population has access to a set of strategies which are indexed by this index j, and alpha j is the fraction of the population on adopting strategy j. And if Sij is the growth rate of strategy j in environment I, then essentially the growth rate of the population will be dictated by this average. See, is it clear? Maybe I should explain it again. So what I'm assuming is that the environment has a discrete set of states, which are the states I, and they can depend on space and time. And in each of these environments, each one of the strategies that the population can adopt has a different fitness. And the idea is what is the best way of distributing the population into these different strategies to maximize the velocity of the wave. So to make this model more concrete, I will first discuss the well-mixed limit. So in this well-mixed limit, there's no diffusion, there's no space, and you have just this exponential growth rate. And fitness, so the population will grow exponentially, but since fitness is a linear function of the strategy, in this case, you will not have any bet-hedging. So what happens in this model is that you will pick the optimal strategy all the time, so the one that maximizes the average fitness, and you should never observe mixed strategies. But now, okay, let's see what happens in space. And instead of keeping the models in general, I would rather try to consider a more specific scenario. So the scenario considered is where there are only two possible environments and two possible strategies. So we consider essentially an adverse environment and a favorable environment. And the phenotype can be a risky one or a safe one. So the safe phenotype is a phenotype that doesn't care about the environment. So that's the same growth rate independently of what happens outside. And the risky phenotype would have a higher growth rate in the favorable environment, but a lower growth rate in the adverse environment. So essentially tuning this parameter alpha, which is the fraction of the individual that's in the risky phenotype, would be tuning how much risk the population is willing to take. And again, instead of considering an environment that changes in space and time, we just consider these two cases separately. So first we consider an environment that changes in time, but is constant in space, or we consider the case in which the environment is frozen in time, but varies in space. So this would be essentially a population that has to cross different territories that are constant, that are unknown, but they are frozen essentially. So let me discuss the temporal fluctuation first. So in this case, we can actually do analytics. So the results would depend on the frequency at which the environment switches from favorable to adverse, and we call this rate k. So if k is very large, then what happens is that the population will feel an average of the two environments, because the switching rate is so quick that I can just average over this fluctuation. And so the velocity of the wave on average will be twice the diffusion coefficient times the average growth rate in these two environments. In the opposite limit of very slow environment, the velocity will be the average of the two velocities, because you would have the stationary velocity in one environment, then the environment will switch, and you will reach stationary solution for the other environment, and so on and so forth. So essentially, the results will interpolate between this velocity, which is the velocity for the average growth rate, to this other result for a small frequency, which is the average of the velocities. So interestingly, in one of these two limits, you will find that you will still have to optimize just the growth rate, which is a linear function of the strategies. But since it's a linear function, every time you maximize a linear function, the maximum will be at the boundary, which means the maximum will always be a pure strategy. So only one strategy will be adopted by the population. So you can see in this top right panel, in this case, the population will suddenly switch from all risky to all safe, depending on which one has the highest average frequency. Instead, in the case of low frequency, you would have a region, and you can compute this by just maximizing this expression respect to alpha, in which the best thing to do would be to have a fraction of individuals playing the risky strategy and a fraction of individuals using the safe strategy. And the reason is that now the function to maximize includes the square root, and the square root is a nonlinear function, and therefore, since there are no linearities, there is a possibility of a trivial maximum in the middle of the interval. So, to study the situation at intermediate switching rates, we resorted to numerical simulations, and this is what we see in these bottom two panels. So the lines are for these 2 points in this sort of phase diagram, and lines are analytical solution, and you can see that upon changing the switching rate, the solution interpolates between these two cases. In particular, if you see in the right panel, you have a situation where for small frequencies, so for small k, the maximum speed is at an intermediate fraction of risky individuals. So we have a non-trivial maximum here, Bet-hedging solution. But for high frequencies, the function becomes linear again, and therefore the maximum is at alpha equal 1. So it's at the end of the for spatial fluctuation, you can make a similar argument. So for high frequency of switching, it is still true that the velocity will be the velocity for the average growth rate. But now, for a small switching rate, what we have to take into account is that the wave will cross faster the territories where the growth rate is higher, and it will move slower in the territories where the growth rate is smaller. And if you do the math, you will find out that this means that the average velocity in this limit is given by the harmonic mean of the velocities. In other words, 1 over average velocity will be 1 over the average of 1 over the velocity in the adverse environment plus 1 over the average of 1 over the velocity in the favorable environment. So again, if you look at this solution look like, you again have this situation in which at high frequency of switch you have only pure solutions, so either alpha equal 1 or 0. But the interesting thing in this case is that you will find, because of this different form of the solution, the region where Bet-hedging is favorable is wider than in the case of temporally varying solutions. So this means that essentially the spatial fluctuation promotes a diversity of strategies more than temporal fluctuations. And this is also observed in numerical simulations. I just spent a few words about the general case. So again, this is a particular case where you have only two strategies and two environmental states, but I can go back to the general case and try to figure out whether this is general. So most of these results can be generalized mathematically to this case. In particular, you can show here that if the environment switches in a fast way, the optimal strategy will be always a pure strategy, so you know that. Whereas for a slow environmental change, there are more opportunities for bet-hedging for spatial fluctuations than for temporal fluctuations. So this is always true. It's not only a particular case of this model with these I guess this is the last thing I want to say. So also in this case, we were worried what happens if you have fluctuations. So this is another model that we are able to study analytically, but we can take the same model with partial temporal dependent growth rate and add this noise term. So what is known from the statistical physics literature is that the effect of this fluctuation is to slightly reduce the velocity. And what it looks like from simulations is that this effect does not depend on the strategy. So in particular, if you start considering this fluctuation, on average, the wave will propagate slower, but this slowdown will be independent of the strategy, as you can see in these curves, and therefore the optimal strategy would be almost unaffected by these fluctuations. So there is a slight reduced velocity, but otherwise the physics is the same. So conclusion of this model tells us that in general, if you have a range expansion and the population has the possibility of adapting multiple strategies, bet-hedging is favored compared to the well-mixed case, because if this model would predict in the well-mixed case, there will be no bet-hedging at all. It's always favored when the environment switches at low frequencies rather than high frequency. It's favored for spatial fluctuations rather than temporal fluctuations. And this effect of demographic stochasticity, so that this stochasticity induced by finite population size, does not seem to play a big role. So there are lots of possible generalization of this model. For example, considering the fact that population, the rate at which population can switch between different strategies is finite as well. And there could be push waves. So these are different kinds of waves where there is a density dependence and so on and so forth. So I conclude my talk. So this is there are several acknowledgements. I would like to acknowledge Paula Villamarti, that is the postdoc in our group, that is responsible for most of the work, especially in the last part. And we collaborated also with Miguel Ángel Muñoz from the University of Granada. And the first work I presented on bet-hedging in jellyfish was done with Nicolas Zagna and Patrizio Mariani at NTHU in Copenhagen. And I want to acknowledge also my founding sources from OIST and Data. And thanks for your attention.
Thank you very much. Questions?
Okay, thanks again for a very nice talk. Two questions. First is regarding to the first part of your talk. So basically you define, you are using the fraction n in your model, right? So if there is an extinction event happen, then either the wild type or the mutant type goes to 0. But
yeah.
n is a fraction, so how do you, it's just a technically quite detail, so how do you take care of that fraction? It cannot be 0, right? Both of them cannot be 0.
So what we do is first we normalize to 1.
Right.
So you have 0.4 of one and 0.6 of the other. So there is first this competition step in which they are normalized to 1. And then we have the extinction on top of that. So if there is an extinction, they all disappear.
Right. So what happened next? So everything is 0 in that lattice, then in the next time step
so
you will have
if you have 0,
right?
Yeah, so if you have 0, at that step there is nothing, but in the next year that patch can be colonized again, either by diffusion or by spawning of these cysts.
Right, but if that's by diffusion, then if the surrounding, because here you are using only the fraction but not the total number of jellyfishes, right? So what happens if there is different capacity of jellyfishes? So the diffusion will be anisotropic. So for some boxes, if there are more jellyfish, you're expecting more amount of migration of jellyfish coming from that direction. But if I'm using this,
essentially, just of course, in terms of general philosophy, this project has been a bit of a struggle between marine biologists who wanted to include lots of details, and I wanted to eliminate as many parameters as possible. Yeah. So, in some sense, we try to find a compromise between something reasonable, but really including only the basic ingredients. So, for example, I think it would be interesting to have, is that what you're suggesting, like the effect of currents. So you can think of having a more realistic map of the ocean, where when it's not isotropic and migration can occur in some directions and not in other. But again, this is really like a basic model to get a sense of why these three strategies exist. So I think then the interesting thing would be to adapt it to more realistic scenario where we know more of the numbers. Right? So I think it's also, to me, this is a field where there is not much quantitative modeling. So this specific problem of reproductive strategies of jellyfish. And in some sense, I think of this model as a first step to sort of start thinking of what could be the underlying theory. But then again, I agree that it's not. I think it contains the basic ingredients, but to make it realistic, of course, one should include many details.
Yeah. The second question is about the second part of your talk. So you do have the illusion equation of f, right? But how about the alpha? Is alpha fixed parameter, or what's the rule for alpha j? Does that change with
okay, yeah, that's a good question. I wasn't very clear on that. Yeah, so what we assume is that alpha j is fixed. Okay. So this means that every time an individual reproduces, it will pick one of the strategies with this structure. So these strategies are not selected, so they are maintained constant in the population. This is a bit of a strict assumption. It's very useful to study this model because since these are fixed, then you can really optimize them. But that's why I was saying it would be nice to think what happens if there is some dynamics of this alpha. So there are some models now. So there are models of bet-hedging where people think these as the population plays a game and picks these three strategies, and these three strategies are constant. Or you can think these are there is some selection over these strategies. So the population tries to adjust them, but if one reproduces faster, there can be a bit of fluctuations. I don't know if that makes sense.
Okay.
Yeah, okay.
Is there any other questions? Question from Stephen? Everyone's very shy. So, may I ask a maybe related question to this slide? So, in the later part, you calculate the variations of temporal fluctuations and spatial fluctuations. Can you explain again how do you calculate? Do you compute it from simulation, or did you also compute it analytically?
So at least in this model, we have these formulas for this. So essentially, the short answer is that in the limit of a very slow switching rate or very fast switching rate, we have an exact theory. So we have this theory which, so you can compute the fitness of any strategy and the optimal strategy. So you can, so this is the expression, and you can express it. You know, you can write it explicitly once you know these functions, and this is in agreement with simulations. In between is just simulations. So essentially, these figures summarize this fact. So the lines are analytical results, and the points are simulations. So you can see that the points essentially interpolate between these two limiting cases, and these two limiting cases are, you know, to the best of our understanding, exact. But for intermediate case, we don't have an exact solution.
Okay. So I guess another question related to this is when you consider the expanding population case, how did you put in the stochastic nodes in your equation? It seems like you use the same equation but just change a sigma. And my question is that the noise is multiplicative, which means the noise term depends on the density. And the growth process, when we expand the population, that process also depends on density. So that means that the noise term would be changed if you have different, maybe slightly different rules of growth, right? So how do you know how do we modify or calculate the noise term?
So you're asking why the form of noise is like this, or how to simulate it?
Why does it look like this, and then when you have different kind of a growth term, and how would that change the noise term?
So I think so. First of all, you can if you formulate the model at the level of individuals, you will have individuals with different strategies, large number of them, and they would move and so on. And you would do like concomitant system size or Lamarck expansion. You can derive this model. So there is a microscopic derivation of this equation, which is essentially as often in population dynamics, you can start with best processes, and then take the population size as large and transform, make a continuous approximation, and make it as a Lagrangian equation. So this is the same but in space. So the other question is how you simulate it, and this is a really nice story, so something I'm really happy to talk about, because it has been, so I was quite lucky because both my postdoc and my collaborator, have a lot of experience in working on directed percolation. And in directed percolation, we have a similar kind of multiplicative noise. And for a while, people were not convinced that the Langevin equation would give you the same critical behavior as the discrete equation, because essentially it was not possible to reproduce the same results in numerical simulation. It seemed that the critical point was a bit shifted, the exponents were not exactly the same thing, and so on. And the reason is that integrating these equations is complicated. Because close to the critical point, since the noise is multiplicative, you really have to be careful on how you, so the integration scheme is quite delicate. So there has been a lot of debate in literature about what is the best way of discretizing this equation if you want to simulate it on a computer. And I believe that now the problem is solved, in the sense that there has been a first proposal that was nearly correct, and then there have been some other papers that fixed some small aspects. But in any case, Paula was able to find read all these papers and understand what's going on, and basically I think now this is possible. So if you, we also tried the discrete model and the continuous model, and then we do the same result. And this is also, by the way, a risk with analytical prediction, so we know exactly what kind of, what is the correction term that this wave should have, depending on the velocity, if there is only one strategy, and you can, you know, the analytical solution matches the numerical simulation, so this is the okay now.
Okay, thank you very much. Yeah, that sounds very interesting. I want to follow up with more details with you. So is there any more questions? Okay. If not, let's thank Professor